Okay, welcome back. If you're starting here, then you need to go back and you need to watch the Narrowband O2 Sensor video that I just finished making, but realized I was going to run out of time for. For whatever reason, my camera stops recording at about the 25-minute mark. So, just to recap where we left off, we had Narrowband O2 sensors that could only tell us if we were rich or lean, but couldn't tell us how rich or how lean we were. So that was good, but it was certainly not ideal. Somewhere in the early 1990s, I believe the first one came out in 1994, or it was finally put into production in 94, in a Honda by the way, we came up with this wideband O2 sensor technology. So, as the name would imply, this can read a wider range of air-fuel ratios. So a narrowband, just to back up, only could read right around 14.7 to 1. Anything above that was too lean. Anything below that was too rich, but we had no idea how. If you fed that engine a 13 to 1 ratio, it said rich. If you fed that same engine a 10 to 1 ratio, it still said the same thing, rich. If you fed that a 6 to 1 ratio, and there was liquid gasoline pouring out the tailpipe and it was misfiring, it said the same thing, rich. So that's not really helping us any when we want to get accurate air-fuel control. So the wideband O2 sensor could actually tell us actual air-fuel ratio and report that accurately to the computer. So if we're trying to maintain exactly a 14.7:1 ratio and we start running at 15.2 for a moment, this thing can tell our computer, you're at 15.2, so the computer knows exactly how much fuel to add. If it starts going down to, say, 13.6, it can say, hey, you're at 13.6. It knows exactly how much fuel to take away to get it back up to that 14.7. So by being a little more accurate and being able to tell the exact air-fuel ratio, we get a much better control over air-fuel ratio. Okay, by having better control, a couple of things are going to happen. We're going to get better fuel economy. If we're burning less fuel, and the fuel we are burning is burning cleaner, we're going to get better emissions. And hand in hand with these two things, we're going to get better performance. More power. And everybody likes more power. Okay, so it's kind of beyond the scope of this video to describe what's actually taking place inside a wideband O2 sensor. There's some crazy stuff going on there. Some of the technology is similar to a zirconia O2 sensor, an old narrowband. Oxygen still does go inside the thing. It does still need to reference outside oxygen. One of the funny things about how they do it, some of them, and I don't have one here to use as an example unfortunately, but some of them, you'll actually see this wire sheath is molded right into the sensor. It actually pulls its oxygen in through this jacket. So you got to make sure that this jacket is never like pinched off or like zip tied tight to something, because that can actually affect how the sensor operates. So we have this wideband O2, still kind of in the same place and still sort of doing the same job. It's in the tailpipe. Some of them look a little bit different. Some of them still have this little louvered shield on the end of it. This little metal cover here with little louvers to let the exhaust gases pass through. Some of them have like a secondary shield and sort of like a little bump on the end. And there's some holes, real tiny little holes right in there. Like if I unscrewed it and looked at it head on, it would kind of look like this. So that's up to the manufacturer how they build it. There's some different styles. It's still going to have sort of a protrusion in the back. There's going to be a wire sheath coming off of it. And then it's going to come to a much bigger plug than we're used to seeing. There's going to be 5 or 6 wires So, as you might guess, 2 of those wires are for a heater. These are always going to be heated. So, I'm in a lousy spot here. 2 for heater. The other 3 to 4 are going to be for your signal. So you might also guess with different technology and a different range of operation, we're going to get a different signal out of this. So flash back to narrowband O2 sensors. If it was a zirconia, it made 0 to 1 volt. If it was a titania, it varied resistance, so it really didn't make a voltage at all. This thing here has a couple of signals going back and forth between the computer. One of them is a voltage, and one of them is a current. So 2.6 volts is what you'll typically see on a GM, and 3.3 volts is what you'll typically see on Toyotas and other things using Bosch technology. And that voltage really doesn't change. It stays very steady. So unlike a narrowband signal that went like this all the time, rich and lean and rich and lean, narrowband, unlike that, this is a basically steady voltage. And it doesn't really change. So you might think, if the voltage doesn't change, how does this thing report the rich and lean air-fuel ratios that it's seeing? That has to do with the current seen in a couple of those wires. It's not looking at the voltage, it's looking at the amps, and it's an extremely small amperage. It's down in the milliamps, possibly even in the microamps. It's very, very small. So if we were to back probe these wires and look at it with a multimeter or with an oscilloscope, the signals we would be seeing there would be very, very different than what we're used to seeing. So it's one of those things where you're going to have to read the service manual and find out how they want you to test this thing, and you're going to need a scan tool. And when you get a scan tool hooked up to the car and you read the sensor data, it may actually be a corrected value. It may tell you current. It may not tell you current. It may just kind of show you this voltage. It may also show you a voltage that looks like an old-fashioned narrowband sensor. The scan tool is doing that, not the car, not the sensor, not the PCM. The scan tool does that for us technicians, so that we can diagnose it a little more easily. It basically puts it in a language we're used to seeing. So if the sensor starts reading rich, it's going to go up above 0.45. If it starts reading lean, it's going to go down below 0.45. But that's not really the actual signal. That's not what's going on in these wires, and that's not what the PCM looks at. So just something to kind of keep in mind. So you'll see different voltages based on different manufacturers, so you're going to have to read the manual there, and you may not see these voltages at all. You might see some kind of, I don't want to say a bogus reading, but sort of a translated reading, a reading that's been translated into something we can interpret, something we can use. So, to sum up, a wideband basically just kind of works over a wider range of conditions, so therefore is a little more accurate, a little more useful to us. This is the more modern technology. I think I already mentioned not to kink or crimp their harnesses in any way. Another thing I should mention, in the older days of narrowband O2 sensors, you could actually find a universal sensor for sale at the parts store. Don't ever buy those, by the way. But you could buy a universal sensor, and it came without a plug. And you would splice it onto the plug from your old sensor, which was handy, as long as the reason you were replacing the sensor wasn't that your old plug was melted or destroyed in some way. You can't do that with a wideband O2 sensor. These things have to be specific to the application you're putting them in. And one of the reasons is there's electronics in that plug, in that connector. Specifically, there's a calibration resistor in there. There's a little resistor that calibrates this sensor at the factory, and that resistor goes with that sensor, not with some sensor that you hack the plug off and splice to this thing. So if you splice a different sensor in here, it's not going to work. not going to work properly. So, back to the whole replacing sensors thing. If you're replacing a sensor, my recommendation to you is always use an OE sensor. OEM, Original Equipment Manufacturing, is best. There are many quality aftermarket companies out there. You've heard me say the name Bosch. They make a lot of the factory sensors and they do sell them aftermarket as well. Another company you might have heard of is NTK. They're a division of NGK. NGK making some of the finest spark plugs out there. NTK makes some of the finest oxygen sensors out there. And there are others. There's tons of other brands, and I'm certainly not able to think of and name all of them off the top of my head, but when you buy an oxygen sensor for a Ford, if you're buying it at a Ford dealership, they're giving you the OE sensor. You know it's right, you know it's going to work properly. When you go to the Chrysler dealership, you know you're getting the correct sensor for your Chrysler. When you go into an aftermarket parts distributor and they sell you an aftermarket sensor, it may or it may not be exactly calibrated correctly for the car. Lots of people buy them, and lots of people have good success. I've also seen some issues, shall we say, where we had running problems or strange drivability issues that we couldn't figure out, and it turned out to be the aftermarket sensor didn't jive properly with the factory electronics. Put a factory sensor in, problem cured. So, as a former flat rate technician, my time is valuable. I don't like to take chances with parts if I've had failures in the past or I've had issues in the past, so I go with OEM on oxygen sensors. There's a lot of parts I don't buy OEM. I have no problem with aftermarket parts, but this is not one of them. So OEM sensors for me. And if you're going to be replacing them, first of all, you need to know how to diagnose them. And second of all, you need to know where to find them in the car. So I'd just like to take a minute and talk about sort of the labeling of sensors in the car. So let's say this is my engine. So we got a V6. Here's the front of the car. My exhaust is going to come off one side of the engine and either go underneath or over the side of the transmission and come around the back. And then I've got my other exhaust manifold here. And at some point these are going to have to combine into a Y pipe. And I'm now regretting drawing this way, wishing I had drawn it the other way so I had more room. But when it comes to a V engine, we have banks. We have bank 1 and bank 2. If you notice, this cylinder is just a little further forwards. That's going to make that cylinder number 1. It's the furthest away from the transmission. So that makes this side of the engine bank 1. And it's different for different cars. That would make this bank 2. So we're going to have an oxygen sensor here. Definitely regretting drawing this picture this way. And we're going to have an exhaust oxygen sensor there. We want these nice and close to the engine so we can detect the air-fuel ratio. This one is what we're going to call HO2S. That's heated oxygen sensor. 2, 1, and we're going to call this one HO2S 1, 1. So you might think that's an 11 and that's a 21, but it's not. It's a 1, 1 and a 2, 1. Yep, major regret how I'm drawing this. I'm going to erase this in a second and start over. So HO2S 1, 1. That's bank 1, sensor 1. So the first one says what side of the engine it's on, that's the bank. The second one says which sensor it is. And by which sensor, I mean, where is it in the system? Is it before the catalytic converter, up close to the engine? Or is it after the catalytic converter that I ran out of room to draw because I'm a dummy and I put this on the board in the wrong way? So I'm going to erase this, make this a little clearer. And we're going to label our 4 oxygen sensors. Okay. Transmission here, skinny little transmission. Exhaust manifold, another exhaust manifold. One's bigger than the other. Okay. Catalytic converter. Most cars have a catalytic converter for both sides, if they're a V. Some don't. Some will combine their exhaust systems into a Y pipe before the cat, and they're going to have slightly different setups of oxygen sensors. Basically, a sensor here is going to be HO2S21. This one will be 11. A sensor back here after the cat. Suddenly my exhaust pipe turned red. Is going to be HO2S12. So bank 1, sensor 2, because that's cylinder number 1, so this is bank 1. And you guessed it, a sensor over here is going to be HO2S22. Okay, so as we established in a previous video, the oxygen sensor helps us figure out our air-fuel ratio, gives us feedback so we can operate in closed loop. The oxygen sensor after the cat is there for a different purpose. It's basically there to monitor the catalyst and make sure it's working properly. And that didn't come out until OBD2 came out. When onboard diagnostics, 2nd generation came out, one of the mandates was that we had to monitor the cat for performance and we had to set a check engine light if it failed. So basically all these guys are doing back here is looking at the cats and making sure they're working properly. So these downstream or after cat, I'm going to write this up here. This is a mess. This board is a mess. So this would be bank 1 upstream. HO2S12. This would be bank 1. Downstream. That's after the cat. So that sensor's only purpose is to monitor the cat. So this one is for air-fuel ratio. This one watches for cat performance. And if your cat is underperforming, your car is going to set the dreaded P0420. If you've ever gotten that code, then you know why I drew the frowny face there. That's an expensive fix because you need a new catalyst. Okay, so depending on your exhaust configuration, you might not have 2 banks at all. You might only have an inline 4-cylinder engine or an inline 6. You don't have 2 banks of cylinders. You probably won't have a sensor 2, or 2-1, but you'll have a 1-2 and a 1-1. Or you actually might see an inline divided into 2 banks. Nissan was popular for doing that. They would actually split the exhaust coming off the engine. And you'd actually have two banks, even though it was, well, you'd have two sensors, even though it was a single row of cylinders. So they would actually combine half of the exhaust and put a sensor in it. And then they would alternately combine the other half of the exhaust and put a sensor in there before they ultimately combined both halves of the exhaust system. And then after the cat, they put one more. So you'd actually have bank 1, sensor 1, bank 2, sensor 1, and then after the cat, further down the exhaust system, you'd have bank 1, sensor 2. So just one of those things you might run into. So if you're ever in doubt on these things, there's always the service manual, there's always Mitchell or All Data or some kind of factory service manual you can read. Whenever you're in doubt, you know the saying, read the factory manual. Find out what's actually going on. How is it labeled? So if you read in there, they will tell you how these things are set up and how they're labeled. But the basic ones you need to know: 1, 1, 1, 2, 1, 1, 1, 2. 2, 1, 2, 2. Okay, so bank 1 upstream, bank 1 downstream, bank 2 upstream, bank 2 downstream. So hopefully I cleared that up after that terrible picture I drew on there. And I think we've hit all of our talking points, all the things that we needed to cover about oxygen sensors: narrowband zirconia, narrowband titania, and wideband. All right, folks, hope you enjoyed it. Hope you learned something from these lessons, and I'll talk to you soon.